If you lived in a major city in the mid-1800s, you lived in a world of extreme density, where thousands of people shared narrow spaces with no functioning way to remove their waste. In Stockholm during the 1850s, male life expectancy was just 20 years. Nearly half of the children born in the city died before their first birthday. These cities were effective incubators for disease. With most residents relying on shallow local wells for drinking water, recurring outbreaks of cholera and typhoid moved through the population with almost no resistance. During this period, major cities functioned as demographic sinks. They only grew because a constant stream of people arrived from the countryside to replace the high numbers lost to infection. Without a shift in public health, this cycle of urban growth was living on borrowed time. The scientific perspective shifted in 1854, when John Snow's study of a London cholera outbreak proved the disease was being transmitted through a specific contaminated water source. To fight back, Stockholm began installing a network of slow sand filters and miles of pressurized pipes to distribute water directly into homes. The results were immediate. While those using traditional wells still faced lethal risks, the data shows that for households with filtered water at home, cholera mortality was virtually eliminated. But physical barriers are vulnerable. A shift in the filter bed or a crack in a pipe can allow pathogens to enter the supply unseen, leaving a city's population exposed to a microscopic threat. Verifying the water's safety presented a logistical wall. Testing for every known disease pathogen is a slow, expensive process, far too slow to provide the daily data needed to protect a growing city. Engineers had the pipes and the filters, but they still lacked a way to confirm that their defenses were actually working in real time. By the late 1800s, researchers like Theodore Escherich and Theobald Smith began looking for a faster way to confirm water safety in the lab. They realized they didn't need to find a specific disease. They just needed to find the universal signal that water had been contaminated by human waste. They focused on a group of bacteria called coliforms, specifically E. coli. Because these bacteria live in the intestines of warm-blooded animals, their presence in a sample is a reliable indicator that feces and the pathogens it carries have entered the water. E. coli works as a proxy because it exists in high concentrations and survives in the environment much longer than many of the pathogens it represents. It's easier to find, cheaper to test for, and provides an early warning before more fragile diseases disappear from a sample. This pivot to proxy testing provided the intellectual shortcut that allowed public health monitoring to work for entire populations. The test moved from a scientific discovery to a national requirement. By 1914, the U.S. Public Health Service adopted the coliform count as the official standard for drinking water. This standard allowed every city to verify, on a daily basis, that their filtration systems were successfully keeping contamination out of the taps. This logic eventually formed the backbone of modern environmental law, becoming the foundation for the Safe Drinking Water Act and the Clean Water Act, providing a legal framework to monitor everything from municipal taps to industrial runoff. Today, these same proxies tell us when ambient waters are safe for recreation, with coliform levels dictating when a public beach must close. By standardizing the proxy test, we legally enforced the safety of the urban environment, making the modern, high-density city a viable place to live. While this system secured our cities for a century, we are now facing threats that the coliform test wasn't designed to catch. We've discovered a blind spot. Certain durable viruses and protozoa, like Cryptosporidium, can survive the chlorine and filtration levels that typically kill off our E. coli indicators. In 1993, the water system in Milwaukee met all legal bacterial standards, yet a resistant protozoan slipped through, leaving 400,000 people ill. Our modern landscape is also increasingly zoonotic. Many of these emerging threats come from agricultural runoff rather than human sewage, meaning our historical indicators for human waste are no longer enough to guarantee safety. The combination of physical infrastructure and proxy testing remains one of the most effective tools in the history of public health. But to maintain this protection, our indicators must continue to evolve, moving beyond simple bacterial tests to account for more resilient, non-bacterial threats. Proactive monitoring is the invisible price of urban life. The goal is to identify the signatures of contamination at their source, ensuring the water stays safe before the first person ever gets sick.